welcome again to our new video. And this video is going to be about meshing that we generally do in structural analysis. Meshing is generally done in case we want more finer results, or we want to study a particular object, or you can say a structural element more precisely when we talk about displacement, axial force, and all kind of things. So generally, what is meshing? We are going to see a basic, you can say, a knowledge about it in this particular video, and I'm going to demonstrate it that how we can use it in Etabs and Staad Pro. Staad Pro is having a basic algorithm for meshing. It generally does the purpose. And Etab is kind of a more refined way of doing it. There are other softwares in market also, which are capable of doing this thing at a very good level. So for this particular video, because it's going to be on basic, it's going to give you a basic idea about it. So I'm sticking to the basic softwares like Etab and Staad Pro. So let's move ahead. First of all, before moving forward, we need to understand from where this meshing words comes in and what is the concept behind this particular thing. So this video is going to be like into the three part. Onto the first part, we are going to understand what is finite element analysis. Meshing is being part of, you can say, the finite element analysis, as the word generally knows, finite element, the small element. Then we are going to see what is a mesh. If we are doing meshing, then what is the meaning of mesh? That we are going to see explanation, elements, nodes, the mathematics behind it. I'm not going to be into the deep. I'm going to be onto the surface, and we are going to see how we can solve the problem with help of this particular thing. And then at the third point, we are going to see the best practices, that what are the things that we need to fix in order to see the result that we decide. And at the last, I'm going to make the model in Staad Pro and Etabs, and then we are going to compare them. Okay, so let's start. First of all, let's understand that what is finite element analysis. So by understanding finite element analysis, we are going to see what is a mesh. Okay, so finite element analysis it's a computational method, and it is used to predict how structure will respond. That what we actually do in our bachelor's in structural analysis and the solid mechanics and all. But this is a step forward. It involves dividing a complex structure into smaller manageable elements. Okay, so we are going to divide a particular object in very small parts, and then solving equation for these elements, and then assembling all the results to understand the overall behavior. So if there is a slab of, let's say, 4 by 4 meter, then we are going to divide it into some smaller parts. Like for this video, we are going to do it 1 by 1. So 1 meter by 1 meter of element of mesh sizes are going to be there, and each of those meshes are going to be solved by our solver. So in that particular case, we need to understand how that particular thing is going to be. So first thing is going to be discretization. Now discretization means the breaking down of a structure into finite element that I have just explained. It can be in triangle form, it can be in quadrilateral forms. Okay. Then there is going to be mathematical modeling. This modeling is going to be done by the software into the backend. There are algorithms for it. It is different for different softwares, and it takes time. The finer the mesh, the longer computational time is required. Okay, so and then we are going to do the simulation, and at the last we are going to use it. Whatever, we can use it in aerospace, automotive, civil engineering, but this video is particularly aligning towards the structural analysis, that is civil engineering. Okay, so now let's see what is mesh. Okay, so how this mesh word is going to be there in our this particular video. So mesh elements are small discrete shapes such as triangle, quadrilaterals, or tetrahedron, and even it can case for a hexahedron in case of a 3D. So these elements represents the portions of geometry allowing the calculation to be performed locally. So there is going to be a set of equations going to generate for that local you can say behavior. Then all of the behaviors are going to get combined, and the result is going to be seen onto the screen. Similarly, there is another thing that is known as element and node. So you can see onto the bottom side of bottom left hand side that when these two you can say elements are getting joined, that point is known as node, and the element itself is that particular mesh. Okay, so nodes are the specific point located at the corner or the edges or the interior of the mesh elements. Okay, and the physical quantities like displacement, stresses are going to be calculated at this particular node. Okay, so this is how the thing is going to be there. So see, the meshing can be a bit complex also. It can be a bit simpler. When it is going to get simpler, when we don't want on more of, you can say, precise, we just want a simpler thing like Etab does. What Etab does, it it includes a default, you can say, mesh setting for the slabs. So even if you don't select the meshing option, it is going to mesh it in a default portion, and it does it very good. For the starting purpose of work or for the low story work, you can use that particular mesh. But if you want, you can say, the desired result, like there is a stress concentration somewhere, you want to give a specific attention there, so then you can change that particular thing. Okay, so let's move forward. Now, what are the best practices? The first thing is that we must have to understand that uniformity. If our model is going to have a uniform mesh, then computational time is going to get reduced and we are going to get the accurate results. But there are situations in engineering problems that when we can't use a uniform mesh for the whole structure. Like just I have shown it here onto the second point, there's the refinement and critical areas. So we need to apply the fine portion where the high stress gradients are there, or just understand it like that. If we are having a beam to column connection and it's kind of having a bolted connection and there is a movement or a load at that particular point, and we need to see that how that particular connection is going to behave. In that particular portion, we are having a stress concentration. So or suppose we are having an opening in a slab. Okay, so in that particular case, the result is also going to be the stress concentration. So at that particular, we need to use the finer mesh. Finer means the size is going to be small. Okay, like I told you earlier, 1 meter by 1 meter by that. The finer means it is going to be more fine, like 0.01 meter by 0.01. Can go like this. But keep in mind one thing: the finer the mesh, the more time will be needed for the analysis purpose. Similarly, coarser mesh are going to be used where there is less variation. Okay, and we need to maintain the mesh quality. The thing is that the aspect ratio must have to be 1. Like I said, 1 by 1, so 1 divided by 1, that is length by breadth, is going to be 1. So we need to keep the aspect ratio as 1. The smooth transition must have to be there. If we are having, you can say, different sizes of meshes, then the variation from finer to coarse must have to be linear, or you can say it must have to be transient. Okay, it must have to be like jumping from fine to coarse. Okay, now avoid distorted elements. We need to avoid the distorted elements. If element is wrapped, is having a poor angle, we need to add it that particular mesh. Okay, so that is the good thing. Stud gives us a choice of, you can say, editing that mesh, but Etab doesn't give us choice. Etab just gives the that how much in which part you need to divide. But in Staad Pro, it gives you whether you want it quadrilateral, whether you want it in triangular, whether you want it in sizes. So both have advantage and disadvantage. We are going to study in the particular demonstration point. Okay, so we will start the demonstration now, that how we can use this particular thing in Etabs and Staad. There are other industry softwares also, like ANSYS. It is one of the best. Abacus is there. They are kind of not that much simple to, you can say, understand, or you can say it is going to study. But this Etabs, SAP, and Staad Pro and FEM, it is kind of simple. You can easily do it. And one thing is there, that is there is a lot of mathematics behind this particular topics, that is finite element analysis. Lot of maths. It includes the matrices, determinants, stress tensors. We need to solve a plenty of, you can say, the partial deflation equations or ordinary deflation equations, and we have many of, you can say, the methods of analyzing the stresses and strain. That's a whole lot of, you can say, methods in the market for that particular thing. I'm hoping my aim for this video is to just to have you have a look about this particular topic, that is meshing, that is finite element, as what it is and what what it provides us, and in market what are the things that are going right now. Okay, so let's start the demonstration. I have already made a simple frame here in you can say the Staad Pro and Etabs. I'm sharing the screen. I hope the screen has been shared. This is a simple, you can say, 4 by 4 of, you can say, a bay frame, and this is 3 meter high, and we need to put a slab over it. So I'm going to select and I'm going to hit the plate cursor to see if there is any plate there. There is right now no plate, so we are going to make it one. So go into the geometry. There is an option add plate. You can just click on add plate and you can just click there and you can make a plate. But instead I'm going to do what, because we need meshing here, so there is an option parametric models. I'm going to click on this particular thing, and then we need to, you can say, make a mesh. So click on add here. Now click on this portion, click here, click here, click here, and click at this starting point. So now there hasn't been mesh has been formed. You can give any name. I'm going to give you the name mesh slab here. Type is slab, subtype let's give it undefined. Meshing type, here it is asking if you want a quadrilateral or a triangular. I'm going to go in with the quadrilateral. Boundary conditions, connectivity means it is going to automatically see that what are the boundary conditions. If there are beam, slabs or like columns are going to be that. So you can go with the none or optimize or define. You can also define like how many number of segments of boundary it is going to be. I am at this particular point, I'm going to use the optimize. It is going to do it by automatically, and that is the target element size. Now target element size, the same thing. That is in what portion, or you can say in what L or B of ratio you need to divide that particular slab. This slab is 4 meter by 4 meter. I need it to be divided into 1 by 1. That is, it is going to be divided into like 4 by 4 blocks. Okay, so 1 meter is going to be 39.37 something inches. So I am going with the defaults. If you have any, you can say openings, you can create that particular thing. I'm going to press OK. So you can see it here. The mesh has been preliminary generated 1, 2, 3, 4, 4 onto the length side and 4 onto the other side. Now there is an option right to the bottom, that is merge mesh. When I'm going to click merge mesh, then the mesh is going to get generated. So I'm going to merge mesh. Now the mesh has been created. Now the mesh is having all of these parts. We need to assign properties to them. Okay, so let's go into the property. Let's go onto the prismatic section and make the column as 0.300. Sorry, not here. In rectangle, let's make the column 0.300 by 300. That is 300 mm by 300. And go on to thickness and give the slab as a thickness of 150 mm. Okay, I'm going to add it. Now let's select our property of beam and column and assign to view. It is going to assign to all the beams and columns in the view. Then let's select the plates and assign to view. Assign, yes. So whatever plates are there, it is going to get assigned. Let's go into the material, double click on concrete, and let's say we are using M25 concrete, which is having a 25 Newton per mm square of compressive strength. So 25,000 kilonewton per meter square. Okay, I'm going to assign it to view and done. Let's go to the supports. I want to assign supports. Let's create a fixed support. Now let's just cover all the supports and then assign to selected nodes. The supports has been assigned. Okay, these are all the basic things. If you don't know about all these things, just check out my Staad Pro tutorial list. Let's go to the load section, click add and click and dead load. I'm going to increase my speed a little bit. Now into the dead load we need to assign a self weight first. Let's self weight, and let's take a floor load of -3 kilonewton per meter square. And for the Y range it is going to be at 3 meter. For the X range it is going to be 4 meter and 4 meter. I'm going to close it. So I'm going to assign it to the view, that is the self weight, and this is going to be our floor load. I'm going to save it. So let's just save it, save. And onto the analysis, define command, and let's just add all and go to run. Now keep in mind the meshing has to be done in this appropriate steps. If you are going to skip any of the, you can say, the steps, then it is going to get distorted. Okay, now let's go to the post processing mode. And I'm going to take this dead load. I'm not taking any combinations right now. Just go to the plate results. Into the plate results, there is a stresses type. These are the kind of stresses that Staad Pro supports. That is von Mises stresses, absolute stresses, and all that. At this particular time, we are going to check the von Mises stresses, maximum von Mises stresses. I'm going to press apply and I'm going to press OK. This is how the stresses are going to look like. Let's go into the view and see the top view to have a better look. So you can see that into the center we are having a red, that is we are having 0.853 Newton per mm square of, you can say, the stresses. And when we move outwards, the value is going downwards. Like the yellow portion, it is 0.6, and then onto the blue we are having 0.3, and at last we are having 0.07. So the maximum stresses are in between, and at the outer portion the stresses are going low. It optimizes it. It considered that the supports are fixed, or you can say the slab is fixed onto the column, so there is going to be no stresses at that particular moment. Okay, so this is how the Staad Pro is going to do this thing. Let's go into the Etab and try the same thing. Now into this particular thing, what we are going to do, we need to create a slab. So go into define section property slab, and there is a slab option. This is slab 150 M25 concrete. This is 150 mm thick. I have already defined it. Let's just go into the quick draw slabs and select the slabs from here and assign it over it. Okay, Now we need to give it a meshing. So click on this particular slab, go on to assign shell object, go on to floor auto mesh option. Here you can see there is a default option, but onto the bottom we are having a mesh object into the size, that is we are going to divide it into what, 4 by 4, because 1 1 1 is going to be like, so it is going to divide it into 4 parts by 4 parts. You can also type it 100 by 100 or 1000 by 1000, but remember that is going to give you the accurate result, but that is going to take you a lot of your time. So I am going to write 4 by 4 here, and I'm just going to apply and OK. So you can see there is a written over here, that is mesh 4 by 4. We can just apply all the loads. I hope I have already applied the loads. No, the loads has not been applied. Select the slab, assign. We are going to go into the shell loads and a uniform, and let's take a load of 3 kN per meter square. Apply, OK. Because we need to make both the objects same, so that's why I'm applying the same load. Let's go on to the analysis and run analysis, and we are going to analyze. All the things are same, that is also 4 by 4, the column sizes are same, the slab size are same, even the loads are same. So that will be a better for us to, you can say, the compare that what are going to be the values and what are going to be the, you can say, the stresses and all of these things. Okay, so the analysis has been done, the deflected shape is here. Now let's go on to the stress diagram, that is shear stresses and stress. And here we are going to see the shell stresses, and we are going to see the absolute maximum, and there is an option of one missile stresses, that is FEM. I'm going to apply it, and I'm going to press OK, and let's see the upper view, that is the plan view. I'm going to press OK. So this is the diagram. Okay, let's take a cut, or you can say let's take a screenshot of it.
So what I have did here, I just taken the screenshot of both the results from the Etabs and the Staad Pro, and I have placed them alongside like one by one. Now into the Staad Pro and to the Etabs, you can easily see that the results of the Etabs are much more, you can say, defined. The contour, or you can say the gradients, are going very fine in comparison to the, you can say, the Staad Pro. If you want to see the Staad Pro under the Staad Pro thing, you can see it here. That is the red one is the in between portion. It is going to have 1.853 of, you can say, the stress, maximum stress in Newton per mm square. And onto the Etabs it is 1.2 or something at like at near to 1.2. Kind of the values are going to be near 1 Newton per mm square, or you can say 1 megapascal. And when you move forward towards the support, the values are going to get decreased. That is in Etab also it is going like 1.04 and then 0.96 and 0.8 at the corners. And in the Staad Pro same thing is happening, that is the values are going to get reduced. Okay, so the thing is that both the softwares are going almost the same results, but Etab is going to show the results a bit finer. When you are going to focus on the supports, it is going to give you the more of the stresses there. That is, it is going to keep in mind about the hogging moments there, and it is going to give you the more finer results. So the meshes are going to be fine, the results are going to be very much fine in comparison to the Staad Pro. See, Staad Pro can be used for the small residential buildings, like if you are having a very small project and the stresses are not that much, you can say, having a very big concentration there. So you can go for the Staad Pro for the lower story buildings. But when you are going to for the tall buildings, or when you want more refinement in structure, you want more of the analysis, or you can say the better analysis, you can go for the Etabs. So I hope you got to understand the basic concept of this meshing.